topic called analytical animation with new views on physics. And hopefully we're going to come to an understanding of this new graphic representation of information. And maybe I should just spend a while right on this starting slide so we can really understand it. The animation itself is front and center top sort of thing, and this is literally adding one quaternion to another quaternion over and over and over again. Okay, so this is probably a collection of, I don't know, maybe 600 quaternions. But what I found was that if I got into more complicated situations, I didn't understand the animations I got out of it. It's like, I really think our brain will have trouble doing things with animation, being analytical about animation. What I found it easier to do was deal with this pretty complex plane. So I have this time versus y, time versus how much up and down. I've got time versus z, it's going into the board, and time versus x, which is whether it's left or it's right. And then what I did was I took every single one of those images and I merged them all together to make that thing that's in the upper or right corner. That's the superposition of all possible states. And I hope that sounds vaguely like quantum mechanics. I'm hoping it actually is quantum mechanics. When they say the wave function, I point to that. And then they say, well, if you actually go and look, out of all these possibilities, you're going to get one of those things that's linked right there. So it's possible that we've got a real technical picture of the wave function, and we've got a picture of the collapse of the wave function a bunch of times. And further, though, and this was one of the things that I got out of doing all this prep work. I realized that that's really more classical quantum mechanics, as it's called, not relativistic quantum mechanics, because if it was relativistic quantum mechanics, I'd have to be coming in from like 16 different directions, and I'll get to that later, but that was one of the results I got out of preparing for that. Okay, so... oh, there it is. Okay. Exactly. It's determining this. Okay, so I mean, we'll get a much better feel for this when we see the software at work. So let's talk about René Descartes. He's a classic French guy or what. His contribution is one of the longest lasting out there. Analytical geometry. Take this equation, here's the picture. I love those pictures. I can see stuff going on. It feels so real and concrete. And so then Newton comes along, actually Newton before. Newton said that time is completely separate from space. And he said that because his math forced him to say it. Now, that is happening. And it was Einstein who said that time tends to space. He's got his light flown separating the past and the future. But it was Minkowski who actually said, no, in a math sense, it really is this one located reality. Sure. You haven't seen that before? Okay, well that's an important picture to appreciate. If changes in time are exactly equal to the changes in space, then you are traveling at the speed of light. Now, in this room, we're not. Well, what does that mean? It means the amount of changes in time are far, far larger than our changes in space. We just sit around and we're talking and talking. And I actually have a piece of artwork to go to do this very separate. Where if I'm talking, moving very fast, we get a few chances to talk to each other, and then that chance is gone. So there's this continuum of hanging out, changes in time to huge compared to changes in space. And then making this progression to the point where we get the light that changes in time are exactly equal to changes in space. Well, when you're talking about how fast are we moving, we always have to say relative to. Okay? You and I sit in this room, yeah, we've got a little bit of movement relative to virtually nothing. Okay? So we just sit around and watch our clocks to the left. That's the point I want to make. Oh, yeah. No, and as a matter of fact, you are moving relativistic to cosmic radiation. You're at 0.99% to what you do on. So you're moving. It's kind of a funny idea. Well, I haven't quite gotten so that 45 degrees is the way we're trying changes in time to get changes in space. And what's cool about that is that anything inside the light cone, it means that you could get to it intuitively if you put in enough energy and work. But if something is outside the light cone, you can't get there. Okay? That doesn't mean it won't influence you at some later time. You know, they might throw a spitball at you, and it might hit you eventually. Okay? And as a matter of fact, I think that basically classical physics is all the physics that is actually within the width of this line. In fact, it's probably a million-fold smaller than the width of that line. That's where all the classical physics actually happens. And it is my kind of speculative interpretation that classical quantum mechanics happens kind of in the width of the space-time. Okay? In other words, those things that we can never reach, they still are there, and they're still going to kind of affect us. And what can we say about them? Well, we're actually pretty limited in what we can say, but we can say very precise things. And I think quantum mechanics is the study of the precise things we can say about events that happen along that sort of line. And then relative to quantum field theory is in the rest of that space. So I hope that gave you a little bit of the sense of light. All right. So I'm thinking about Quaternion as events in space-time and four numbers that you can add, subtract, multiply, divide, and do all kinds of things. And let me actually just demo the software for just a bit here. So I'll bring up. So this is all software that I've written, and one thing about the software I wrote is that I'm a big fan of the command line interface. Are you familiar with that? No? No, that's okay. Yeah. Here you are. Okay, good. All right. So command line is things that you just type. You just type a few letters, and it'll spit back stuff. And the reason I'm a big fan of this is because computer technology, you may have noticed, changes rather quickly. And if you say what has lasted like 30 years, it's basically almost nothing, except the command line interface. And why is that? It's because you deal with small commands. And those small commands are, they're small, so they're robust. It's not like I've got this huge, stack of software. And secondly, I can type the results of one command. One command does one thing, and I can, let's call it type, into another command that does something else. And so what you do when you do that is you can come up with permutations. And so you get kind of the power of permutation with small commands. Now one command does this one. Now one command does that one. And I can pick the result of one, type it into another, type it into the third, type it into the fourth. Okay? And how many possibilities can you do? They're pretty linear. So, and I didn't like the idea of investing, say, in Java and then finding out that Java was changing and changing and changing. I wanted to build a tool that I could come back in 5 years and 10 years, and it would still work like it did when I wrote it. So you just one of those instructions command. Let me show you an example. I preface these commands with Q1 just prints a 1, a 0, a 0, and a 0. Okay, that's not a difficult command. I've got a Q0, which will do the same. But if I do LSQ, yes. See, so these are all these quaternion commands, taking arc sine, exponential, Q random, et cetera, et cetera, et cetera. So, but actually, yes. Or, yeah, they're all C programs. They're all C programs is actually what I should say. So if I go Q add 1, 2, 3, 4, 5, 6, 7, 8, it comes back and says, oh, that's 6, 8, 10, 12. And if I go and I can basically then take that result and pipe it into the Q sine function, and I get some numbers back, and I go, I have no idea what that means. Okay. But one of the more important ones is called, constant linear motion. Let me just see what it reads in one integer and 8 real numbers, and it just kind of makes a whole series of them. So let's do 4, 1, 2, 3, 4, 1, 1, 1, 1. Let's see. No, that's not. Oh, okay, yeah. So it started at 1, 2, 3, 4. It took 4 steps, and it ended up at 1, 1, 1, 1. Okay. So if I think that work is 4,000, or the 4,000 steps between now those two numbers, I can now take those 4,000 between, type that into the Q sine function and go, boy, am I really confused. But the point is that I can make a whole pile of different. Okay? So you say, why would you do that? Because, actually, let me just change this command just a little bit to, let's make this to 10. So this is going forward, and this is going from a time of 1 to 10. You see, this is nicely ordered. But what if I now take this and pump it into one of those Q sine functions? And you go, oh, this is bouncing all over the place. And, well, what I do with my animation software is I say, I'm going to sort these based on this first number. And then there's the minus numbers, the smallest, so the biggest minus number up to the biggest positive number. And then I am going to say, put this in a 10-second film. Okay? And based on this number, that will decide which of the frames in the film it will notice. And then once I'm there, I'll use these two numbers, the X, the Y, and the Z, to decide where my little yellow dot is. So if you do that, then it means you can use a program like Q polynomial, I believe I got here. Q poly. Let's see what it says. Okay, so it basically you can get to you can start to now create a polynomial, a quaternion polynomial, and have it generate a bunch of quaternions, and then make an animation out of that. And once you can animate the polynomials, you can animate anything. So actually, let's see if that command works. Whether my help notes were okay. So it's, I think we're saying any. Oh, let's see. Copy. No, I didn't copy and paste right. So let's just skip that. but at least conceptually, I should say I consider this this bit of software I've written somewhat user hostile. Okay, it's not a really slick interface, but at least for me, it's been pretty powerful. So that's kind of an introductory sense of the software. All right, so this one we should know about. Quaternion addition is an inertial observer. So this is the simplest kind of operation you can do, and yet it's very deep because it's connected to such a relatively very directly. So, oh yeah, this to me is really fun stuff to think about, because we think we understand real numbers and complex numbers. I mean, the way it gets taught is that simply we've got the real axis, over here, and we've got the imaginary axis over here, and there's just this 90-degree rotation. That's been taught for an awfully long time. And there's something unsatisfactory about that because we know this has different properties than that. And yet there's no reason why they have different properties. Yes, they have different properties. I accept that. I know it's a very productive thing to do. It's just, I wish I had a picture of it. I think that now we will. All right. So all I'm doing with this animation is I'm going from the corner pocket up to 0, 0, 0. That's all I do in this one. So this is the same sort of common thing, but I'm really when I come to, so there's my time, and we're pointing it up to the 0 time, and then this is it. Okay? This is the setup. Okay, so now what is this? What I am doing is doing a reflection in space. Formally, I'm taking the conjugate, and what you can see happening here is that I have this mirror reflection going on. So it's like something, I've got a mirror, and I can see that when I get to 0, it goes away. All right, so, and visually, when I do this conjugate operation on my conjugate in blue, the conjugate is in blue, I always see 2 strings on the top, 2 dots on the string, which makes sense. It's a mirror reflection. All right, so now I am doing a time reflection. So instead of having time be positive, I'm having time be negative. And so when I do that, it looks different. It comes up to 0, and then it goes and takes a step back. So that visually is different. I mean, it's the real number that's getting responsible. When I put an imaginary number, it's mirrored, and I can see that. When it's the real number being put, I see it going forward in time and reverse. So events go in exactly as they come out. So now I'm doing all 4. Okay, so it appears like there's this continuation going on. So I've got in yellow, that's my input. Okay, the green one, the blue one is a reflection in space. And then I can do a reflection just in time, or can do a reflection in time and in space. So the continuity of this is kind of thing you can share after a while. Like you said, but it does take a while. Okay, so if we think about the yellow line going into, say, the red line, the yellow sitting on the red, who we see? He's the one who reflects, does both mirror reflection and the time reflection. Okay? And so, let's see, the one that's in blue, that is the space reflection, and he goes on to the one that's a time reflection. So it's fun to see the connections between these things. And all we've done so far, asking questions and flipping a few times. It's tricky. It's tricky. You can see why I enjoy this. Like, how do you make this figure 8? Well, I took a circle in, I took a sine of sine with a 2 over 2, so 2 over 2 in sine, and so wow. And you know, from a sense, it's doing the circle in 2 pi for this guy, 2 pi for that guy, and it's got to work hard because of that factor too. It's got to go 4 pi in order to do this sort of thing. And my critique is that there's really no need for supersymmetry. So supersymmetry is this tool where it says, oh, I've got to get something that has spin 1 and spin 1/2, and how could I possibly have a particle do both of them? These animations like this say it's not a problem. I'll put whatever kind of symmetry I want to in one of the x's or the y or the z. I can combine them.
So this is a reality more information that you can consider feasible?
I think the point I'm trying to make is that you can do, because people like to think of things as being in separate boxes, and that when you really think about time and space together, they really can do more in your little room together. I mean, I didn't expect to get a figure 8. I just said, I know how to generate this. I have no idea what it's going to look like. I certainly was surprised that it came out of the figure 8. I was certainly surprised that it certainly looks like a hyperbole. Okay? But it's actually a finite hyperbole, which is another thing I hadn't had experience with. When I draw a hyperbole, they have to extend out to infinity. But, a circle doesn't extend out to the infinity. And by the way, every moment here is reflected in there and is reflected in there.
What I was getting at is matter is, in a sense, spatially confined energy. When you really get down to it, it's nothing more than the distortion of space-time that you're feeling and it's all about. So what we consider reality, meaning mass, energy, all of this, is nothing more than math. I mean, when you're dealing with a mathematical representation, it may be what it is.
I had somebody who said to me once, I thought it was space-time. That's like vague enough to be true. Okay? And that's how I feel about it. And I don't mean to be insulting. It's not. It definitely is along that line. This graph is just trying to say, it's almost like what happens with clouding. How in the Olympics, they're spinning this many axes along this axis, and they're spinning that way on that axis, and they're doing on the third axis. I think there's a lot more possibility. I just don't see the need to keep the strength because I think I have to say separate about this. Really quite simple. It's not that.
So what is this display you have to replace supersymmetry with?
I think I haven't done that, in a sense. In other words, supersymmetry really is the formal body of physics work. Okay?
You're the only participant in this conference. Press any key to continue this conference.
Yeah, because I did.
Press any key to continue this conference.
Particle physicists are profoundly stuck.
Press any key to continue this conference.
That's the wrong thing. There's no presenter. Sorry about that. So what is supersymmetry?
So the particle physicists are really stuck. They can't figure out how to get gravity in with the rest of it. And we take my point of view with it. Okay? Because I think the future maybe it isn't stuff. I could say I'm only using the Quaternion math called tensor math. Okay, thanks to the same darn thing. That's the way I got the math right. Exactly. I mean, I got to be straight on two straight. Not exactly. Okay? They are profoundly stuck because there's no way to get from that to a theory of gravity. You can get to a theory that works really, really good. That's general relativity. It works really good. Okay. But we're drawn to exercise, which a little bit I digest, but I hope you like this digest. So we're drawn in for general relativity. There's U naught, because I can write it down here, and I bet you can remember it. It's one letter long, okay? That letter is really hard. I don't completely understand it because it's the contraction and the contraction of the Riemann curvature tensor, which is like way up there in the sky as far as figuring out and understanding. But if you go, why can't general relativity get along with the standard model? We go, this guy is in his room by himself. He doesn't care about anybody else. There's nothing else here. You'll also hear very often, oh, general relativity is really elegant. It's amazing. Well, it is. But there was Riemann level. But this one isn't going to play with everybody else. Okay? So, the particle physicists working with only effectively Quaternion can't get to the theory of gravity because they're not going to go use hypercomplex numbers, which are even less popular than in Quaternion. So so given that box that I think there is, okay, they're saying, okay, what can we conceivably do? And you have a lot of basically the brightest people on the planet, and what can we possibly do for years? And they came up with an idea. And that idea was supersymmetry, where every particle that we know, and we know is about 400, has now a partner, a superpartner, okay? And that superpartner, well, we haven't seen one yet, but it will allow us to do and think all kinds of new ideas. And that's hard to think about. I mean, I can't follow when they talk about it, okay? But it's a serious technical effort to get the standard model to do stuff that is worth the craft. And I think that's probably not a physics system. I just know they have to double all the particles out there. I know that they're looking really hard for it. And that's another one of the things that they're trying to do in the Large Hadron Collider. We've got $10 billion on the line. And we really want to see the Higgs, we really want to see a superpartner, and then we will suppose that there are lots of others. But until they find the Higgs, and until they find the superpartner, it's anybody's guess what's going on. And it's the true with W secondary.
sound more like a polynomial than for your say where we understand that something that's not really right and broken, and yet the whole person a little package to it, is really incredibly complex. When in fact we just had it wrong.
That's almost like I think that you got to end up that way, right? There's a lot of sincere genuine effort with strength. And I haven't insulted those people, okay? They are hard workers. They are in a similar kind of bind. They, in fact, work off of supersymmetry, and they do other things beyond that. And to me, when you start animating, just one, two, or four numbers and really put them in a pile and start looking at it, these don't look like things I'm used to. And I'm kind of taken aback by it. Really. So I don't think we have explored good old 3 dimensions. I shouldn't say 4 dimensions. This is another one of my little tweaky things. Because if I say 4 dimensions, it sounds like it's 3 dimensions plus another dimension. Okay? That's a little misleading. And it's important you get your fundamentals right. Because 3 dimensions, those are pointy. Those have the arrowness to them. That's 4? No. The 3 dimensions of space and a scalar, time. There's no pointiness to my plot. Okay? That's what I'm dealing with. It's not 4 dimensions, a scalar and a 3 vector. And if you keep that in mind, then you don't get into a, why don't I go up to 7? Why don't I go up to 10? Okay? Because how did the scalar go? Oh, the scalar didn't go. It was all n. So that's my own little thing. So,
but also every time you go up, you eventually start from all the basic words of algebra.
Here is that true. But what I was saying, I have had the most wonderful time in my own head dealing with 3 dimensions of space and time. And so let me give you just another super concrete example. Here's this group called SU2. It is a group that is involved with the weak force. Okay? And if you say to someone who's really professional out there in group theory, what does that look like? They're like, what do you mean, what does it look like? It doesn't have a look. And you go, but it's only using 3 numbers. Shouldn't you get some picture? Can't you get something out of it? And what they can write down is they can write down a Quaternion exponential function, where you take the Quaternion and you minus its conjugate. That's basically a way to knock out the scalar. You knock out the scalar, you have 3 numbers, and you just take the exponential of that, and that will always have a normal 1. Because it's like e to, if you say what's its norm, it's like e to the I, and e to the minus I makes up e to the 0, that equals 1. Okay? So math-wise, this is rock solid. And that's as far as they go. I shouldn't say that's as far as they go. There's very sophisticated, there's interconnections between these various things. But they won't say, let me make a, okay? And I said, I want to make that. And so what I did was I just took random Quaternions. That's what this represents, actually. I took literally, 10,000 randomly generated Quaternions. Using 2 random 1,000. Okay. Then I typed it into this function called Q vector, so I would throw away the scalar. Then I would type that into Q exponential, and then I got this pile of numbers. And to me, it's profoundly wonderful, ironic that you see this pile of numbers go by and you say, I have no idea what this looks like. And then I've got another piece of software that says, okay, thank you for generating that. I will make you the sum. And this is what we get out of it. And it took me a while to understand. But it's good to start with these shadows. You see the shadow in the animation? Okay, it's basically starting in about 8 different points. Okay? And the points are going to grow into each other and connect and make circles, and there's a sphere that goes and down. This is another profound philosophical aspect of this, is that everything is finite. And so So I just keep on cycling it so I can start to get it. Okay, so what happens is you start to say, this final point I understand. That is, that's when the space part is shrunk to nothing, and all I have is a time component. And that time component, where is it in space? Because it's basically moving 0, 0, 0. So all this activity is like, and where it reaches its maximum distance right there. Okay, that's a very valid question. So I've got the value of t, the value of x, the value of y, and the value of z. And those are the numbers. Alright? So what I do is 3 pairwise graphs. Actually, let me use my thumb for this time, so that's easy. Time and x. That time and x goes in this particular. Time and y goes in the other one. Time and z goes down here. And when you glue them all together, now, no, this is something I don't have the ability to really. I don't have the ability to go, oh, because I see what's going on in these three, I know it's going to be go on in the animation. I don't have that ability.
Isn't there really an emergent nature in this field? Do you really think about that possibly?
It's one of those things, maybe you became an expert at this, eventually you'd be able to, yes. So I look for much simpler things. I can hold on to these simple things. It's like, I start out with nothing. Something's coming up. Okay, there's some kind of turning point now, and everything's going to fit. Those are the three things I get going from the complex thing to what goes on in the animation.
It's highly determined. So what word do you use to describe it? You have a highly deterministic, it could be of a somewhat chaotic nature.
It's not
a fairly emergent nature.
I think it feels emergent like that.
Emergent.
Yeah. So Gadget here? Yeah. Because of the way that this is generated, I use 10,000. If I would have used 100,000, it would have gotten to these numbers.
So there was much different if they used 1,000.
Yeah, well, it looks more vague.
Was there a point that was much over point? Would 20,000 be any different from this, or would 5,000 be any different from this?
I would say that there's a transition from this is really kind of rough to that smooth.
And what would that number be roughly?
It depends on the rock. It really depends. And it probably also depends on how big a ball I throw into my 3D program. Because, conceptually, these are all events. But how big should I make my event? If I make it super small, I'm going to need a lot more points in order to see it. So part of that definition is to do the size of the series that I have to choose.
Do you have a program so you can play the 3D like on the new 3D?
Not yet. I really watch that technology because it's like, I got my 3D things and I want to see it. But I haven't made that move yet. Okay, so, this is SE3, which is on your t-shirt, right? This is the star of that one. And what I love about this one is this looks like a uniform, tennis ball at the game. It starts, it gets out to the edge, and then it comes back in. And it's also, to me, philosophically satisfying, because I'm trying to say that that the three symmetries that show up in the standard model, that would be this one, U1, that would be that one, SU2, and that would be this one, SU3. What that really means is that I'm an observer. Where am I as an observer? I'm at 0, 0, 0. 0, 0, 0, and something happens in space. Okay? And they go, well, how far away was it? They're like, I don't know, I'll just call that 1. It'll have some x to it, it'll have some y to it, it'll have some z to it, it'll have some time to it. Maybe it was back of me, maybe it was in time, maybe it was in the future. Okay? Whatever that was, and I don't even know what caused it, it's on this unit sphere. This is an animation of the unit sphere. And yet I connect it to the symmetries that are the standard model. And it feels like I'm done. You know, I can't do kind of more than this, which is cool, because that's what the limit on what, you know, the limit that appears in the standard model. It's these three groups, it's only these three groups, it's not more than these 3 groups. And I go, yeah, because we're trying to deal with the unit sphere. Something happened in nature, and somehow it gets all connected. But it starts to get a little hand-wavy, okay? And I admit that. In other words, I have no idea what's the strong forceness of this, okay? Instead, all I have is I see those groups. They're really there. And they're really forming a life object that I can understand. I can understand it's true. So, wow, there's hope there. But there's hope there, and there's also not hope there. You remember how you said, why don't you publish it? But where am I going to publish my animations? It doesn't work as a PDF, ever. Okay? It's like, that's weird, I do. Okay, so, this was the thing with the gamma matrices that show up in relativity quantum field theory. And believe me, those are scary. But if you go on like this, you see. And the idea is you can start with one path, and in my software, I put it on both sides by the 1 and 1 K, and I take the same selection from the other thing, and start with an I, with a 1 K, all 16 possibilities, and lo and behold, you end up with this. And so that is why quantum field theory, in my opinion, is going to be so hard to exactly the heart of it today, and will remain as long as people study it. Because it's hard to think about all the possibilities out there. And yet, apparently that's what the math machine is about. The math machine is really shows and looks at all the different ways you should take those two X, Y, and Z values and mix them up. It bothers me that this one knows how to mix things up like that. That's interesting. Oh, sorry. This thing? But not in exactly the same four corners? Yeah, okay. That was a design decision, you see how this doesn't quite go to the center? If I went instead to the center, it would look prettier. It would look a little less off. Where exactly that started also, so I wanted to make sure the T, X, Y, and Z values that it started with were a little bit different, and that they didn't quite go to the origin, and that's what makes it have that scattered look. In other words, if you went dead on, T's with Y's and the rest of the Z through the origin, I think you would end up with maybe 4. Right the difference. But I didn't want to, do that. So I think what we'll do is spend a little bit of time maybe looking at a couple more animations that are available on visualphysics.org. I want to go through the number theory stuff and then get a sense from you guys which one of the other things we go through, because you got to get your what number theory looks like correct. I think it's important. So one of the most important things is that real numbers are boring in terms of animations. So real numbers, so we've got a minus real number and two positive real numbers, and they always are at the origin. Okay, so maybe it's going up there. Blink, a little bit of dot, and now blink, 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 blink. And they never move left, they never move right. These things are paralyzed. And there's kind of a very funny, I think it's funny, personal story connected. Okay, so I'm becoming this expert in determinism. Okay, so what's the value of that? Okay, so I'm unemployed for like a year. Okay, I'm like everything every time. A friend of mine says, a friend of his, that I'm going to do through school, and he says, I'm looking for smart guys. So this guy actually drives up to see me. And this was in a time when absolutely nobody had GPS. Yet people had it. I don't know why. And he's one of these guys who's designing financial models of things. You know, deals with very large amounts of cash, and all you have to do is take a slice, a little bit of sliver of that, and that's a lot of money for you personally. And so we're having this little discussion. Me totally out of job. And him totally connected to making a lot of money. You know, you start with 6 figures, the bonus you really want. Okay. And he said, oh, so you do your own thing? I said, yeah, I'm going to pretend. You ever heard of pretending? And he's like, no. And then he's like, happy. And then I said, well, how about complex numbers? I'm sure if you're building these financial models, you know, complex numbers will come in there and say, never get it. Oh man, my expertise is so irrelevant to you. And it is. And it's, to me, it's this profound funding that come out of financial markets. They only care about these thoroughly boring. But remember what I'm doing. I'm treating these as events in space-time. I'm treating the real numbers as time. And so that old thing about time is money, okay? Time is money is boring, whatever. It's kind of a fun little connection. All right, so real numbers, in terms of animation, don't look so great. But how about complex numbers? Well, complex numbers, they can move. They can move, which is good. But they move in straight lines. And you know, if I didn't use, you know, X, Y, and Z formally like this, we use thetas and whatnot, they move in curved lines, however you define it. But basically, it also is kind of soft. Less soft, but still a little bit soft. Now, formally, the next one is addition, but we've done that twice already. And this is one of these ones that just surprises me, even to this day. I'm going to animate norms. Okay, so the yellow is the input. Okay, it's a bunch of different values, and then I do a reflection in space. Okay, so I see pairs. Remember how you have the pairs of things, and then the norm. Well, the norm has an x of 0, a y of 0, a z of 0. So it sits the origin. Okay, so I've always thought of norm as how big something is. When you animate everything you do, then the norm is how old it is. So my norm is actually big. But that's a different perspective, isn't it? And does that bother you for a week? Okay, it's like now norm, I can't think of I got 5, 8. I don't know. I think that's kind of a cool little observation.
How did you make that insight of going from science to music?
This animation? No, I got to tell you, this is the honest truth. The one animation I figured out ahead of time was the Quaternion addition. I said that's going to be moving along the straight line, no problem. Every other one of these, almost without fail, I said I better look. No, whatever I bet on is wrong. It's like my intuition failed me over and over again. And I made that thing isn't moving at all. And it's like, yeah, norms are never, ever, ever. So that's another concept. This is going to give you fun walking around and going, why does that make sense? It shouldn't, but it does. And particularly when you look at the pile of numbers. I should let me do one other thing about these things. No, it's in essence, it's a message from the math. The math says, okay, take a number with three vectors and a scale, do its mirror, multiply the two together, and all of those come together to just give you a scalar. Scalar, no pointiness at all. Okay, and that pointiness in an animation ends up being how old it is.
By pointiness, you mean direction.
Yes.
Vector.
Yes.
So it's vectorness free. Okay. So each one of these, by the way, I represent several different ways. I'm focusing on these things which have three complex planes, the animation, the superposition, and a random sampling of the superposition. And then I know our brains really don't like motion, and so I have these kind of smaller ways of representing them. This is the actual command right there that created this process. So when I say it's a little user unfriendly, but at least it's readable. That's what it took to actually make it. This let's see, iPod. I actually did that. I usually try and include the math that I was actually using, and there are the actual numbers. So that's why I say that it's so amusing to see this endless pile of numbers and say, oh, I'm going to make a film out of this. I'm going to make a film and I'm going to think about it. Its philosophical implications. It's like, really? Okay. So let's go back. All right, so let's take a look at some polynomials. Okay. So here's a second order polynomial, and this is also a great example of why I use a complex plane. The complex plane is just that scalar with a t or a c with an x or a y or a z. It's because when I say I want to see a second order polynomial, I want to see something that's got a vector. This yellow is the input. That's what I'm putting in, and I get the red thing out of it, and it's got the vector thing. I like that. Okay. Let's see. Is this animation? I might crash my computer. Is my computer getting confused? These are all GIF animations, which is not a really fancy technology, but it was one I could figure out how to, program in.
What do you usually when you get the animator? You just finish your step.
We just make what is it? 100 frames. I do 100 frames in one day.
So no, the website actually writes the animated GIF file. You don't use the animated GIF program.
So I want to see the hooky thing. Okay? Now, the hooky thing is in the animation, but somehow never quite looks at it. So there's a little red dot, very round, okay? If there was a hook going on, it doesn't feel right. I always feel more comfortable with the static image that shows up in the complex plane. Let's get to things that are even more fun. Let's go to a third order one. So this can have a curve to it. Yeah, stop that. All right, there. Let's see how long it takes it to. I better close down other things going on. Hopefully, it won't get too confused. It's really having trouble. All right, I want to simplify some other things. No, I better do that.
Is what you have running a browser?
Yeah, no, it's just a browser. We're at the website visualphysics, and we're in the Quaternion animation section. Yes, towards the plane. The yellow is always, I shouldn't say always, usually the input. Okay? So, I could, in fact, if I don't go through the words and things, you will get even more confusing. Okay? And then this is the polynomial. And if I look down lower, I see that it is q to the 3 minus 2q plus 4, something like that. Okay? And that feels right in these complex graphs. But look at how crazy this is. Okay? This red dot. This red dot. We get one red dot. Oh, now we have 3 red dots. Now we have 1 dot. Okay? And
There were 3 inputs?
no, I took this input and I created a polynomial out of it. I got a pile of components out of it. And that pile of components looks like this red block. And what this does basically is it's doing this, and at this point, there is, and I'm going to use some language from quantum field theory, there is a creation event. And the creation event has 2 particles go like this. Okay? And then, when we get to here, we use again the jargon from quantum field theory, there's a destruction, annihilation event. Okay? And what's like really crazy, attractive, I can't quite reach there yet, is that those words in the quantum field theory stuff, I mean, they teach you how to use that in the keywords. They certainly never show you a picture. Okay? And they certainly are of this opinion that there will never, ever be a picture. Okay? And I'm starting to think that, no, those are good words. There are possible animation out there describing. So that's what this feels like. I mean, this looks, and the complex plane is very simple. And then when I look at it in the animation, I see a creation event, I see an annihilation.
It's almost feel very reasonable.
Oh, yes. Yeah, we talk about, this operator won't create, particles in these states.
But you have textbooks with stickers,
right? Exactly. And my big dream that could only possibly be, I never did for other days, that there will be a picture of every single one of those things. And this is the first kind of glimmer of that kind of thing. Because I certainly, when I just do the program, here's how I'm going to make my program thing, and I got the command that it's ugly, okay, and I didn't expect it to be seriously in my life.
So you started from the Quaternion, i.e. the math.
Yes.
You guys started from the physics. Where did the physics?
No, that's day 2. You missed day 2.
Okay.
So day 2 is really hard. No, day 2 was quantum field theory equations, just written with becoming machinery. And I should say it was just written. At this point, Brushing looked very different, except maybe there might be more equations to it. But a lot of it is just dead on the standard stuff. Let's see if we got. So let's just jump. Yeah, there are variations on this. Let's see what happens all the way down at the bottom here. Yeah, it quickly becomes so confusing that didn't I make this animation? It was like, yes, and I don't quite understand. Oh, this is the yellow and the red. Okay, this is what the yellow and the red, they go together. Okay, and that's what we just spent so much time trying to figure out what's going on with creating an annihilation. And all I did was I started at the same spot. I just didn't go through the order. Remember how I said I like going through the order and I get residues? I did more degrees by just taking exactly the same out of those. Okay? Just the input doesn't go through the origin. And it ends up creating an orange one. So now I don't have that item section sort of thing. I need this graph job, changing things over here. So, what is, it's like, no wonder we live in such a wonderfully simple, yet confusing world. It's all the methods I can take out. think like, now I've got a good feel for what's going on.
I'll have to look at the together before we can get that.
I don't understand it.
I understand the math that I used down below here. Let's see if I've got that summarized nicely right now. Let's see with the... okay, so it's just Q3 plus 3Q minus 2. And in one case, I go from minus 3, minus 3, minus 3, plus 2, plus 2, plus 2, plus 2. That would be the yellow and the red combination. And now, if all I do is go to a different point, I start the same point. I understand. Well, that doesn't look too complicated. Instead of going with, like the one that it wasn't like, this is connected to something deep in the universe. Really wasn't.
So unlike nanobody, it took me a very long time to get dinosaurs. But at some point, you began to get a little bit of a feel for how the given equations created this pattern of analysis.
Yeah.
Okay. And in fact, they eventually turned it into a product by having software and so on.
Yeah.
So are you at a point now where you really don't, you have a feel for when you do a polynomial and so on, what it's going to unfold into? Have you gotten any guidelines?
I think I'm too much an experimentalist, and my experimental attitude is say, is this important? Okay, if this is important, I want to not put any bias into what I want to look at. I want to make sure I'm touching it right. And so that's why there are maybe 7 or 8 different polynomials to get a feel for some of the important parameters around it. And I've just been too wrong in what the final thing looks like.
Is there any way a possibility of automating your experimentation where you can, it's very easy, you build something that's great and whatever you do. The other end will be something that they have a way of looking at the resulting imagery and saying this has the characteristics to make it interesting.
Well,
you can then do billions of things.
Well, there is just an enormous mountain of software development that could go into it. But I have so many development in there, and it's a fight over what I do next. And I thought about maybe taking a mathematical science to, let's do this in mathematics because that has far more reach than these tools that I have. I know mathematics, quote unquote, can do all this stuff, but it's quote unquote because to me it's important to have all 6 of those things together to get a sense. So you get the sense that I've got the complex things because that looks like I expected to look. The animation specific conditions. It could have all be done. I just haven't made the investment that direction. I've decided to go so that or develop the website so it has no reach.
These kinds of things. Fair question. All right. Yes, it's not dealing well with all these animations. Okay, so I guess let me try and do two more. I'll try to explain these box sort of thing, and then we'll look a little bit into the science because that's let's kill these pages. Kill pages. Let's see if let's open up good old Firefox and see if Firefox does a better job. That's going to be the no. That's going to be the live Stand-Up Physicist live episode. So, all right. So these are basically at this point. These are all the animations that I've made, and this is a 3 spatial dimension and 1 time dimension wire cube. Okay. What is this? All right, so this is what a three spatial dimension and one time dimension cube looks like. And again, I programmed it. I said that's solid with the program to do. These are the numbers. This is what it looks like. Now it's confused. So if you're a little confused now, that's okay. It's traveling a cube with 4 degrees of freedom has 16 points. So 1, 2, 3, 4, 5, 6, 7, 8, 16 points, 16 versions. Okay? And in any cube in this box, what you're basically doing is saying, I'm going to just change one parameter in order to get over here. And then I'm going to change one parameter, in this case y, to get up to here. Okay? But since we now have time, I'm going to go from in time. That's what's going in there. We're traveling in time up to the next 3D solid state, next to 3D sphere. Okay. So this is -1. Oh, we're not at -1 anymore. We're traveling to +1. We're traveling to +1 where I can show you the wire tube. Yep. So that's what travel through time looks like. And formally, yeah, that's what happens. You see the collection of numbers and you go, oh, look, I've got -1 in the time column, and I see my x's, y's, and z's all changes for the thing. And then you see the p, x, y, and z all three, and you flip the time pointer and get changes, and that's what most of the video is traveling from one, what I would call a wire tube, to the next.
In your view, is the piece of time already in existence and then leading back to the present with like a chance to form
I see this is a 10-second universe. Actually, I make it a little larger than 10 seconds. It depends on how big the volume is. I work with volumes of space-time, okay? And so the volume of space-time is a little bit greater than linear. Okay, that's why it starts with nothing and then you see the wave. Okay? So I see this as the formal definition of a cube, which is to think about starting at -1, and just writing all of those, okay? And then saying, hey, from here to there, that's literally, this is the Z, so this would be E along like that. Right? And just doing that whole process. And the ones that go like this, you say +1, -1, -1. The one that is like that, that's one of the dots that appears to dominate the animation. Okay? So I'm looking really formally and going from here to here versus from here to here because this is the scale, this is the timeline that's fitting. And so to get this nicely.
So then does your stuff work just as well if one looks backwards in time?
Yeah, usually that's
okay, so then the notion of forward backward in time is nothing special about going backward in time.
No,
like there's the basis. There are only a few places where backward and forward.
I would have to take a pretty long digression about this, but that is an important issue. And the reason, in my opinion, it's not handled correctly is because you couldn't think about it as a problem in time. No. That's the arrow of time problem and the connected entropy and ability that a lot of people spend a lot of effort on. And I think it's just a poorly formed question. You have to think about space-time. Okay? Space-time has a function. It's the space part of space-time that has attention. And if you do it that way, then that problem isn't there anymore. Well, it's not that it's not there. It's like, I'm trying to make the point about 4-1 question. 4-1 question, give me an answer. What is 1 plus? I hope I don't get that on the test. I will never be able to answer it. And what is the arrow of time? I don't think it's going to ever be answered. And believe me, people, really smart people on the planet have thought about it. They haven't come up with the answer. And I don't think they ever will. But what is the arrow of space-time? And what is the consequences of including space when you start to do that analysis? That, I think, will go very far. But that's one of these subjects that I actually have a very solid first step in, and have never taken the subsequent steps. And there are a huge number of subsequent steps to take. Actually, it was on the board yesterday, but since you all discussed it, there is this thing called the density, okay? And very, very importantly, when you say what element do you need to take an event A and go into the past. So all the things with this time. And the element, so the density is simply minus 1, 1, 1, 1, 0, 0, 0. Great. So you go, what would it take to take half and go back? I bet it's the same thing. You can play ping pong forever, okay? You play your ping pong forever, play a billion times, nothing matters, okay? That, in some ways, is what their problem is that they're doing. And they're not going to solve it, in my opinion. Okay? But they're right. That is a problem. It is a well-defined problem. All right. So what happens if you say A is a determinant, and I'm going to use my big reverser die, and in order to get to B, okay? And say, well, you can do that. Okay? But what if you wanted to go the other direction? Would you have an R die over here that would be, would you just take the same darn thing and in order to get back here? And the thing is that there's a cross product here, okay? And well, I know people have said bad things about that cross product. But that cross product turns out to be wonderful. Because if you deal with, in classical physics, the cross product that shows up in pulling off these operations, and we're not talking gradient physics as far as the objects, we're leaving that data. But the cross product here would be, in a classical situation, really ridiculously super tiny. Okay? So tiny that this thing approximates just being like minus 1. You know? Because you say, I don't have to even care about the vector part of the A die, and so just take it minus 1, and I'll go back and forth. Okay? I'll go back and forth, except for this little residual little cross product dot that's never the same when I go back and forth. So if you do that 100 billion times, okay, that cross product starts to matter. And it's that cross product nature, I think, that makes, that we see every day show up. Okay? But you have to abandon the little.
Adding up like those billion insignificant terms.
Yes. Yes.
But like when you have a Taylor series, and you say, oh, you throw away the D and DD2. You just throw it away. That's one way. The other way is also you can just begin to put in the A to the arrow. Somehow along the line.
Well, that's a fancy thing. That's a fancy thing. But I'm saying it's non-fancy. It's just that time is so much bigger than the space part. Okay? That this is almost like 1. This is almost like minus 1. And so that flips it around. Okay, so Quaternion-wise, I have lambda approximately equals just minus 1, 0. 0 is everything. Okay? That's what my kind of theory was. And it's just like, but it's not right, because this will have a vector, this will have a vector, and if those have little vectors in them, then only those little bit of differences. And when I say little, I mean, you literally have to go over like 10 digits, before it shows up. It's like 10 digits, I'll forget about that, the thermal doesn't.
What does it correspond to physically?
The space time. Yeah.
Is this in a sense related to virtual particle? Is this in a sense related to physically?
Not really. But the thing is, so I have that little observation that, the cross product matrix, but there's so much to thermodynamics, and I haven't connected that little observation to any concrete equation. Okay, I'm going to equate right in equation 2. I haven't made that, look at my reversal thing, and look at this law of thermodynamics. That's a long, much more equation.
These are the things that if you weigh it up, what do we manifest?
The asymmetry seen in nature, which is, that nature is not reversible on a large scale.
You have to get into the kind of asymmetry you see on particles and antiparticles?
I haven't done it. All right, so I wanted to give you that sense, and I wanted to do one other thing with sines and cosines, because sines and cosines are just so important to how the world works, and they just don't look right, at least in my hands. There we go. Trig functions. Okay. So what here we go. These are, let's see, the yellow input, let's see, I haven't looked at this in a while. They have to do with surface. So I fix the x, the y, and z, okay? But the blue one is pointing kind of in a different angle in three-dimensional space than the red one. The red one is actually pointing in different space. And they have different amplitudes. Sine functions you can multiply out big numbers or small numbers to make it small. But they kind of go to different places. So that's. Let's see. Sines and cosines. So maybe I should look at what the equation I'm really dealing with is here. Oh, it's not showing up. Darn.
Why do you like sines and cosines?
Well, I'll tell you why. Because I've been taught, everyone's been taught the same thing. It's like sine looks like this, and cosine looks like this. Okay, I wasn't very accurate with God. But there's a million components of the planet. And I started playing with things, and I did this thing to take -5, the yellow as usual is my input. It goes from -5 to positive 5, and I said, okay, go from -5 to positive 5, type it into Q sign, type it into Q cosine, show me my million damage. And I didn't see this. And even to this day, I don't quite get what's going on. But,
what do you mean by million damage?
That's what I expect to see when I do the thing. And here, well, everybody's kind of in the same, on the same line. So that's one thing that happens. When you deal with sines and cosines, the polynomials that point in the same direction, and so they will always have this, we're on the same line here. But if you force me to say, well, which one is the sine, which one is the cosine, I think I'd get that wrong about half the time, because I haven't gotten comfortable yet with this stuff.
You're really dealing with kind of the first one as you would any other function.
Yes, it's just a function.
Just a function, rather than going back to say something like vibrational ether stuff and saying, I'm going to look at wave equations.
Yeah.
You can get with you.
I just expected to see something like that, and it wasn't even close. And so what I did to make this one was I made the changes in time much greater than the changes in space. And when you do that, you get these nice spirals. In the complex plane, if everybody of you thinks it's just a continual glory, like, oh, spirals in the complex plane, and then you look at the animation and you go, where are those spirals? I mean, they're there, okay? It's the same collections of numbers that are used to make every single point of these things. And you can see why I'm going to have trouble communicating with Dr. White, anybody, even myself. Because there's not a sense of, oh, we've gotten slowed down. Well, I guess you could focus on one dot and say, well, he's now speeding up and he's going to climb faster than the boom. So actually, if I focus on that red guy, he's kind of hanging out, he's going to increase speed, and he's going to crash into somebody sometime. Oh, there we go. So if you isolate one guy, you can sometimes make a transition between what's going on in the complex plane and what's going on over here. But, you know, as I said, I didn't know what to expect when I was increasing changing time relative to the thing in space, and this kind of thing. And you just go, the kind of possibilities that happen with this staggering, you go, well, I'm not even filling up space. I'm just filling up the line, you know? These animations, I guess we really say, okay, let's fill up all space. Well, let's just fill up a line. Really? I would think that it would just have more spirals. That's my guess. Yes. Tighter spiral. Yes. Oh, we got some. All right, so, and this is just signs in many different directions. So this was born out of the frustration of not really filling up space-time very much. And so I just basically chose different values of the three vector parts, the x, y, and z. And so that way, it never looked as crowded in the animation. That's what happens when you start filling space. That makes kind of a look on So, let me just make a couple more points about the website itself. So we've got manifestos, which are supposed to be my overall attitude, tutorials, which hopefully explain how things work. The animation section, which goes through these different maths that I've figured out so far. The downloads has the software that I've gotten to work on Macs, PCs, and Linux boxes. The preprint server is my own preprint server. They're all of 7 pages here, 7 articles. They're web viewable. In other words, you don't have to download and print the PDF. You can go ahead and just read it here. One of the more unusual aspects is that there is also a Mathematica notebook because you can very light, you stuff to go at my math book, and this is my internal check to say that I am providing well-formed math is the idea. And then the new thing is the talks page, which will have all of these, which has day 1 here, day 2, and the PDF of this talk. Although this is more spontaneous than that. The forums is a place to chat, and as I pointed out, I think on day 1, it's basically Doug chatting at this point. It's not a community. We do have, I should say, I do the amount of people asking me about this stuff around the globe is manageable at this point in my life. And so I usually will get back to you in relatively short order if you decide to ask me any question as well. And we are definitely, this is definitely a global endeavor. I know some people in Bangalore were excited about this stuff. But here are all the notes, and there's somebody else who's not on this continent who couldn't be in Boston, and but as I said, we're going to be so it really does have global reach, and that's really kind of cool about it.
How many people know mandatory these days?
Oh, I get an email one couple times a week. That sort of thing.
So how many people do you think in this community that really represent to get involved in it or understand it? There isn't a community. Or I haven't tapped into there are people who do Clifford Algebras. They have an active community and they have a meeting once every 3 years. I went to that once and they said, oh, well, you're just a small section of Clifford Algebras. Oh. All right, so I think we'll end it there, and we'll do the.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass, and all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Quadratic equations. She leans over the desk and twirls a pencil in her hair. Complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
The favorite thing out of this whole thing of the Stand-Up Physicist is just the sound of a mic, thing coming through the amp. That doesn't belong in a classroom, does it? Okay. So, I need my clicker. How can I do the top of the clicker? All right. So first you'll notice that picture actually is not very good, but I am the MIT T guy. When you go through Tyndall Square, there are these two nerds, about 19 years old. One of them holding up a little dish. Actually, they're both holding up a little dish. One's got these teardrop glasses and a nerd watch. That's me. Okay. I am the face of MIT. I hated that photo. It showed up in Tech Talk, and it's been up there for now decades. And so I am the face. But let's go through the 10 slams, top 10 slams. Let's see what they are. All right, so the first slam is theoretical physics grants me too many experiences in humility. Oh. Inflation, the search for a new constant velocity solution for gravity. I don't think Guth would really summarize it that way, but that's that's my own take on it. Dark matter, the search for a new constant velocity solution for gravity. Okay, very similar. And again, I don't think people who do dark matter research would think that was a slam at all. No, that's just nonsense. All right. The future moves, get with the program, analytic animations. That's what you suffered through. Oh, no, that's what you enjoyed today. All right. 6. Wrong ideas can be made arbitrarily complex. See work on strings. and hopefully none of those people are in my audience and will come hurt me later. Okay. The brightest people on the planet cannot explain the simplest shit because time screws with everything. Maybe. All right. black hole math is bogus. If that works out, that there will be more than a few people who are not happy. So I think a lot of people think that comment is bogus. General relativity, good but wrong. Oh boy, we're not going to be popular with that one. God plays with the norms of derivatives. And that was in the second day talk, that claim. And the final thing, I don't need no stinking Higgs. And that is on the t-shirt. So thank you all very much.